This is my intermediate algebra course. Today we're going to continue to learn functions and function notation. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we learned how to find the domain and range of a function using its graph. Today, we're going to do the same thing, but we're not going to be given the graph of the function. We're just going to be given an equation, and we have to find its graph so that we can write the domain and range using the graph. So let's do an example here. It says find the domain and range of the function below. We have f of x is equal to 1 over x, and we know that a fraction with 0 as its denominator is undefined, so x cannot be 0. So finding the domain of that function is pretty easy. The domain is all real numbers except 0, because 1 over 0 is undefined. And we have set notation and interval notation. But finding the range is not so easy. In the previous class, we found range using a graph, but we don't have the graph of this function. But notice that this function seems familiar. This expression is actually found in the library of relations. So if we use the graph of this expression, this relation in the library, we can easily find the range, not only the range, but also the domain if we have trouble finding the domain. In this particular problem, we didn't have trouble with that, but if we have trouble, we can find both range and domain. So let's look at the library of relations. Here's the library, but notice that we're not calling it the library of relations anymore. We're calling it the library of functions. In most cases, when you search for a library on the internet, it's not going to be called the library of relations. It's going to be called the library of functions. The library of functions is exactly the same as the library of relations. The only difference is instead of y, we have f of x. Notice all these f of x expressions there. Get a picture of the library of functions. You'll need that as we work along today. And if you look at the reciprocal function, what we used to call the reciprocal relation, now we're calling it the reciprocal function, you can see the range very easily. All the points on that pink graph, the y values just get bigger and bigger and bigger and smaller and smaller and smaller, and they approach 0 from the bottom and the top, but you can see there's a gap here. There are no points that are on the x-axis. So there are no points that have a y value of 0. So 0 is the only value that is not in the range. So the range is all real numbers except 0. So the range just happens to be the same as the domain. And in set notation, we say the set of all y values such that y cannot be equal to 0. And in interval notation, we write negative infinity, comma 0, union 0, comma positive infinity. And the parentheses mean that 0 is not in the range. So we can find the domain and range of all of these functions in our library just by looking at the graphs. So again, get a picture of the library of functions You're going to need that library as we work along today. And now we're going to practice finding the domain and range of some of those functions in the library. Here we have the absolute value function. Instead of calling it the absolute value relation, we now call it the absolute value function because we have f of x here rather than y. We could probably figure out the domain pretty easily. The range would be a little more difficult, but we don't really need to analyze the equation because we can go straight to the graph. We can see just by looking at the graph that these points, they have x values that get bigger and bigger and bigger, or smaller and smaller and smaller. 0 is an x value of a point here, so you can see that x can be anything. The domain is all real numbers. And whenever you're writing set notation in that case, you write all real numbers in words. And in interval notation, we write negative infinity, comma, infinity. So that is the domain. There's no real restrictions for the domain. But you can see in this graph, there are no points in the third or fourth quadrants. And what that means is that the y values are all positive y values. There's no negative y values. If you had points down here, then we'd have negative y values. Y can be 0. So the range is all real numbers greater than or equal to 0. And set notation, we say the set of all x values, the set of all y values, because this is range, the set of all y values such that y is greater than or equal to 0. And in interval notation, we use a bracket because 0 is in the range, and an infinity symbol, and then a parenthesis. Remember, always write parentheses next to infinity symbols, because infinity is not a number. It's just an idea, so there's no way that anything can be equal to infinity. Also, I want to keep reminding you the smaller number, or whatever is perceived to be the smaller number, again, infinity is not really a number, but the smaller number is written at the left. If you write positive infinity 0 with a bracket, this is meaningless. This has no meaning when it comes to mathematics. Okay, so I want you to try number 2. And so the way that you're going to do this is you're going to find the cubic function, the cubic parent function. And you're going to analyze the graph, and the graph will tell you what the domain and range is. So get a picture of that. And try number 2. And when you come back, we'll do it together. Okay, we're back. The domain is all real numbers. And interval notation, negative infinity, comma, infinity. And the reason for that is that the x values just keep getting bigger and bigger and bigger, and they never really stop. And they can get smaller and smaller and smaller over here. They just keep going farther and farther to the right and farther to the left, the points that is. So the x values can be really anything. X can be 0 also. Now, what is the range? Well, the y values just get bigger and bigger indefinitely, and they get smaller and smaller, and y can also be 0, so y can be pretty much anything. We can see that just by looking at the graph. So the range is the same thing. In fact, I'm just going to copy, and we can just put that there. So if you got that right, good job. Let's try number 3 together. Now we have the exponential function. Again, we're now calling it the exponential function rather than the exponential relation, but it's really just the same thing. But notice that the base is a. I'm just giving this equation an arbitrary base because it doesn't really matter what the base is. The domain and range is going to be the same as long as the base is greater than 1. So let's look at the exponential graph here. And the reason that a has to be greater than 1 is that if it's 1 or anything less than 1, then the graph isn't going to look like this. So notice that the points go to the right indefinitely and they go to the left indefinitely. So that means that if you collect the x values of the points on this graph, it's the set of all real numbers. So that's the domain. There are no restrictions on the domain, but you see that there are restrictions on the range because there are no points in the third or fourth quadrants. So there's no points with negative y values. Also, we know that this graph never touches the x-axis, so there's no point on the x-axis, so there's no points with y values that are 0. So the range is all real numbers greater than 0. So again, the domain is all real numbers, and interval notation, negative infinity, comma infinity. That's the domain. You can take a picture of this and look at this if you want as we go along here. The domain can be any real number, and the range has to be all real numbers greater than 0. And in set notation, we say the set of all y values such that y is greater than 0. In interval notation, we say, or we write a parenthesis, 0, comma, infinity, and then another parenthesis. So I want you to try number 4, and remember, the base of a logarithmic expression. Remember, this little number here is the base. It's not allowed to be negative. So you see here it says a is greater than 0. Again, I'm leaving an arbitrary number here for the base. I don't mean to do that to confuse you, but we're just talking about any arbitrary number there. But the number must be greater than 0, or else that logarithmic expression doesn't really have any meaning. Also, a cannot be 0, or else, or it cannot be 1, that is, or else the graph will not look like this. So get a picture of that graph. You're going to need that graph to find the domain and range. And try number 4. When you come back, we'll do it together. Okay, we're back. So if you look at all the x values of the points on this graph, the x values are all real numbers greater than 0. Why is that? Well, because there are no points over here, so there's no negative x values. So the domain is all real numbers greater than 0. If you got that right, good. And in set notation, we say the set of all x values such that x is greater than 0. And in interval notation, we say 0, infinity with parentheses. Now, the y values of the points on this graph are the set all real numbers, because this graph goes up and up and up indefinitely, and it goes down, down indefinitely, which means that the y values can be negative numbers, positive numbers, or they can be 0. So the range is all real numbers. In an interval notation, negative infinity, comma, infinity. So if you got that one right, good job. So now we're going to find the domain and range of more complicated functions. Look at this function here. That's very complicated. In the previous class, we were given a graph of a function, and we were asked to find the domain and range, and that was really easy because we were given the graph. We could see how the function changes. We could see how y changes and how x changes. But in this problem, we're only given the equation of the function. Now, we could find the domain by doing some algebra here, and we could find the range. The range would be a lot more difficult, but we could do some algebra and find the range. But it's much easier to use a graph, to picture the graph. In the previous problems, we already had the graph because it just so happened that the functions we were analyzing were functions from the library. For example, the reciprocal function. We called it the reciprocal relation in previous classes. Now we're calling it the reciprocal function. The absolute value function, we called it the absolute value relation in previous classes. Now we're calling it the absolute value function, and so on and so forth. But now we have more complicated equations. But that's okay, because we can graph this complicated function here, this equation, using our library of functions as a starting point, and we're going to use the transformation method to find the graph, and once we have the graph, we can easily find the domain and range. Now again, the equations we're starting with and the graphs that we're starting with are all from the library, and this library again is the same library of relations that we used in previous classes. We're just calling it the library of functions now. So you can see that the parent function is going to be the square root function. We used to call it the square root relation. Now we're calling it the square root function. Now, we don't want to use this tedious notation here. As we explained in the previous class, when we show the possible y values, we don't want to have to use that notation f of x. So we're going to switch to y, and that'll make it easier for us to change the form of the equation, because we can't see exactly how to graph this expression or this equation unless we change the form. So I'm going to change f of x to y. And again, that's just to make things easy. You don't have to do that, but I would suggest doing that. Then we're going to take this 2 and put it on the other side of the equation. So we have y plus 2 is equal to the square root of negative 2x minus 3. Now we can graph that relation, and it's very important to understand that the graph of this relation will be the exact same graph of this function up here, because all we did was change the form of the equation. So we're going to start with the parent relation, but rather than calling this the parent relation, we're going to erase and call it now the parent function, because we're using functions now. Obviously, this is the square root parent function. Notice that I'm using y instead of f of x. That's because we switched to y to make things easier for us to manipulate the equation, and we just don't want to keep carrying that notation f of x down, because it makes things difficult as we use the transformation method. We don't want to keep rewriting f of x. It's also important to know that in a function, the output can be called y, and sometimes it's called both y and f of x. In the vertical axis, you'll see y is equal to f of x, meaning we can call the output f of x, or we can call it y. I know that's kind of complicated, but we can call this the parent function, even though we're using y. That's perfectly fine. I know that's kind of complicated, but that's just the way that mathematicians do it, so there's no avoiding it. So we have our reference points, and I know that you're getting tired of having to graph these same equations, but we're doing this for a reason. Partly because we want to learn how to find domain and range, but also because it's not enough for you just to be familiar with the graphs of these equations. You must be completely fluent. You must know them like the back of your hand. So it's okay for us to do these over and over and over again. We're doing that on purpose. You might say, well, I can skip this because I've already done this. No, you cannot skip anything in this course. Okay, so now we need to figure out what the next step is. We're trying to graph this complicated equation. Can we translate first, or should we dilate or reflect first? Well, if we dilate or reflect first, let's say we put a negative 2 in front of the x, then when we translate, we're going to be subtracting 3 from negative 2x. The transformation properties don't tell us what to do in that situation. The transformation properties only tell us what to do when we're subtracting 3 from x, not from negative 2x or 2x or negative x. So we can't dilate or reflect first. We have to translate first. So I'm going to replace y with y plus 2, and I'm going to replace x with x minus 3. And as you know, that moves the graph 3 units to the right and 2 units down. You already know this stuff, so I'm not going to spend a lot of time explaining all this. You have your reference points and you're familiar with these graphs. So now I'm going to reflect. I'm going to replace x with negative x. So we have y plus 2 is equal to square root negative x minus 3, and that's going to reflect across the y-axis. So our graph ends up looking like this. There's kind of a sloppy curve there, but you get the point. So now we're going to dilate. We're going to replace x with 2x. So we have y plus 2. Y plus 2 is equal to the square root of negative 2x minus 3. And now we divide all the x values by 2. So the x value of this point is 3, so it becomes negative 1.5. I mean, it's negative 3, that is. The x value of this point is negative 4. So it becomes negative 2. And now we have to find some more points. So if you plug in negative 6, we get positive 12, and then minus 3 is 9. The square root of 9 is 3. So then we have y plus 2 is equal to 3. Subtract 2 from each side, and we have 1. Sometimes you have to do that. So if you plug in negative 6 for x, you get 1 for y. So 1, 2, 3, 4, 5, 6. and up 1. So now we can connect our dots. So why did we do all that? What was the point of that? We graphed this complicated function up here. This purple graph is the graph of this complicated function. Why did we do that? Well, we did it because we can easily see the range and domain by looking at this graph. Now you're probably thinking to yourself, I don't like this. I don't want to do this because this is a lot of work. Well, when you go into upper math courses, you're going to do most of this in your head. You don't have to draw all these graphs out. And you're probably thinking, well, why do we have to do it now? Well, we have to do it now because you can't read my mind and I can't read your mind. We have to make sure that we're doing this properly. So we have to show the steps. But now that we have the graph, we can see that the domain, which is all the x values of the points on this graph, the domain is all real numbers less than or equal to negative 1.5. The biggest x value is the x value of this point here, which is negative 1.5, and all the x values over here are smaller than negative 1.5. So the domain is all real numbers less than or equal to negative 1.5. And in set notation, we say the set of all x values such that x is less than or equal to negative 1.5. In interval notation, we use a parenthesis, negative infinity, and negative 1.5, and a bracket because negative 1.5 is part of the domain. So now let's look at that purple graph and look at all the points. What is the smallest y value? What point has the smallest y value? Well, obviously this point here. The smallest y value is the y value of this point, which is negative 2. And all of the points above that point have y values that are greater than negative 2, so obviously the range is all real numbers greater than or equal to negative 2. In set notation, we say the range is the set of all y values such that y is greater than or equal to negative 2. And in interval notation, we write a bracket, negative 2, and then positive infinity with a parenthesis. Again, the smaller number, whether it be the domain or range, the numbers have to increase as we go left to right. So if you write infinity over here, and a comma and a negative 2, and then a bracket over here, this notation has no meaning in mathematics. Okay, so that's the general idea. Let's try another one of these problems before you try one on your own. We have a very complicated function, and we're asked to find the domain and range. Now, we could just use the equation, but it might be a little difficult to figure out what exactly the domain and range are using the equation. So what we're going to do is we're going to get rid of this f of x so we can manage the equation without having to rewrite that f of x. Also, we want to recognize, or we want to relate this to the library of relations which we've been using in previous classes. And we want to put this negative on the other side. You can divide both sides by negative 1, or you can multiply both sides by negative 1. You'll get the same result. So we put this yellow negative on the other side of the equation. And now we can graph that relation, but we're not going to call it a relation anymore. We're going to call it a function. So we're going to graph the parent function. So obviously the parent equation is the exponential equation. And again, we could write f of x, but we don't want to. Y can represent the outputs of a function. So we can just write y. That'll make it easier for us. And remember, exponential relations always have a horizontal asymptote. Plug in 0, get 1, plug in 1, get 3, so on and so forth. Connect the dots. You've done this many, many times. So now the big question is, what do we do first? Do we translate, dilate, or reflect? And the answer is we can translate first or we can reflect first, but we cannot dilate first. If you dilate first using the transformation method, then we're going to get the wrong graph if we use the transformation properties the way they're written. And the reason for that is if you replace x with x over 3 in yellow up there, well, at some point you're going to have to add 2. You're going to have to translate. But if you do that, you're going to be adding 2 to x over 3. The transformation properties don't tell us how to change the graph in that situation. We know what to do if we're adding 2 to x, but we don't know what to do if we're adding 2 to x over 3. So I guess we'll translate first. Again, we can translate or reflect because the reflection happens on the other side of the equation. So y is equal to 3 to the x plus 2. I'm replacing x with x plus 2. And so that moves the graph to the left 2 units, which has no visual effect on the invisible asymptote line there. But all these points are moved 2 units to the left. Okay, so now that graph is kind of sloppy, but you get the point. And so now we're going to reflect. Again, we're trying to graph this equation here. We're going to replace y with negative y. So that reflects the graph across the x-axis, which does not change the position of the asymptote. And we get the following graph. So now we're going to dilate. So I'm going to replace x with x over 3. And what that does is it multiplies all the x values by 3. Again, that's not going to change the look of the horizontal asymptote. Sometimes dilation, translation, or reflection can change the position of the asymptote, but in this problem, the transformations don't move the asymptote at all. But you do need to be aware that many times the asymptote will change position. So we're going to multiply all the x values of the points in the previous graph by 3. So the x value of that point is 2, or negative 2, so we're going to multiply by 3 and we get negative 6. So this point goes there. And the x value of that point is negative 1. So it's going to go here. And let's see, any other points I think would be off the, any other points that we can find easily would be off the window. So I'm just going to connect the dots. Your graph doesn't have to be 100% accurate. We just have to get the general idea of what's happening. So now that we have the graph, we can find the domain and range of the function. This graph here is the graph of this complicated function up here. So what is the domain? What are all the possible x values of the points on this graph? Well, this graph, actually, it doesn't look like it, but there is no asymptote here. It just keeps going up and up and up and up and up and up and up. Actually, I mean down, down. Down, 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 down. It just keeps going forever. So it'll keep going off to the right as it goes down, and it'll keep going off to the left indefinitely. So the domain is all real numbers. In an interval notation, we write negative infinity, comma, infinity. Now, what is the range? Notice there are no points up here. So all the points have negative y values, and this graph is going to approach that dotted asymptote, but it's never going to touch. So there are no points on the x-axis. So there's no points that have a y value of 0. So we say the range is all real numbers less than 0. And in set notation, we say the set of all y values such that y is less than 0. And in interval notation, we write negative infinity, comma, 0 with the parentheses, because 0 is not part of the range. Now I want you to get a screenshot or a picture of these problems with your phone, because you're about to do 2 of these types of problems. So you can use these 2 problems as a guide. I want you to try number 7. So you want to change f of x to y, and then you want to put this negative symbol on the other side of the equation. And then you want to graph using the transformation method. And once you find your graph, you can find the domain and range using that graph very easily, and write in words, set notation, and interval notation. So again, you may need your library of functions. We used to call it the library of relations. You may need these problems to help you. Try number 7. When you come back, we'll do it together. Alright, we're back. So again, to make things easy, we're going to change f of x to y. Just makes it easier for us to keep rewriting the equation. And now we're going to multiply both sides by -1, so we have negative y is equal to x over 3 minus 1 squared. We could divide both sides by -1 also, because this negative is multiplied into this yellow expression here. If you forgot that, a lot of students forget that that's multiplication. We're multiplying the -1 by the x over 3 minus 1 squared. So instead of calling this the parent relation, we're going to call it, again, the parent function, because we're dealing with a function now. And the parent equation is obviously the quadratic. So y is equal to x squared. And we'll draw our reference points and connect the dots. Your graphs don't have to be perfect. They just have to have the general shape there with the correct points. Now we need to figure out what we're going to do first. Are we going to dilate, or are we going to translate, or are we going to reflect? In this case, you can translate first, or you can reflect first, but you cannot dilate first, because we cannot subtract 1 from x over 3. Well, we can do that, but the transformation properties don't tell us what to do in terms of changing the graph. But if we subtract 1 first from x, that tells us to move the graph to the right 1, and then if we divide 3, if we divide x and x only by 3, that tells us to multiply all the x values by 3. So I'm going to reflect. Again, you can translate first if you want, but I'm going to reflect, and we should get the same graph. So that reflects across the x-axis. And then I'm going to subtract 1 from x. And that moves 1 to the right. And then I'm going to replace x with x over 3. And we need to multiply all the x values of the points of the previous graph by 3. And we get the following graph. Now we need to, well, I guess we can use this point here. That point is negative 1, 1, 2, 3, 4, negative 1, negative 4. So that becomes negative 3, negative 4. So now I think we're ready to connect the dots. We might be able to find another point over here. Maybe we can plug in negative 6. If we plug in negative 6, well, that's going to be off the window. So that's probably good enough. So now we have the graph of this complicated function here. And we can see the domain. The points, they go off to the left indefinitely, and to the right they just keep, the x values keep getting bigger and bigger, or smaller and smaller. And so there's really no restrictions on the domain. The domain is all real numbers. And the range, we can see, is restricted because there's no points up here. The biggest y value is the y value of this point here, which is 0, and all other y values of the points are less than 0. So the range is all real numbers less than or equal to 0. Because 0 is in the range. In set notation, we say the range is the set of all y values such that y is less than or equal to 0. And in interval notation, we say, or we write negative infinity, comma, 0 with a bracket, meaning 0 is part of the range. So if you got that one right, good. Try number 8. Remember, when you have a 4 right next to a logarithm, that means 4 times the logarithm. So you're going to have to divide both sides by 4. But remember, first change f of x to y. And you're going to graph that complicated function using the transformation method. And once you get that graph, you'll be able to see the domain and the range. So try number 8, and when you come back, we'll do it together. Okay, we're back, so we're going to change f of x to y, just so it's easier for us to move the equation around. We don't want to keep using that tedious f of x notation. So now we're going to divide both sides by 4, so we have y over 4 is equal to log base 2 of negative x plus 2. And now we're going to graph this complicated equation using the transformation method. Obviously, the parent relation is the logarithmic relation, but we're not going to call it a relation because we're dealing with functions now. So it's the parent function. But we can still use y for the output. That's okay. Mathematicians are okay with substituting y for f of x. So we know that this equation has a vertical asymptote, And if we plug in 1 for x, we get 0. That's always the case. If we plug in a number that's the same as the base, we get 1. So if we plug in 2 for x, we get 1. And then we need to start plugging in powers of 2. So 4 is a power of 2. 2 to the second power is 4, so that means we go out 1, 2, 3, 4, and up 2. 1, 2, 3, 4, and up 2. And we're ready to connect the dots. Again, your graph doesn't have to be perfect. Okay, so the big question is now, what do we do? Do we reflect first? Do we dilate, or do we translate? We can't reflect first, because after writing a negative on the x, we would then have to add 2 to negative x. So the transformation properties don't tell us what to do when we're adding 2 to negative x. They only tell us what to do when we're adding 2 to x and x only. So we're going to either dilate first or translate first. I'm going to dilate first. So I replaced y with y over 4. And that's not going to affect the vertical asymptote. So we're going to multiply all the y values by 4. That doesn't change this point. But this point has a y value of 1, so the new point is going to be 2, 4. And maybe we can plug in some other values, but I think we're going to go off the window. If we plug in 4, we get 2 here, and we get 8 for y. So that's going to be off the window, it looks like. So I'll just connect the dots. The graph doesn't have to be 100% accurate. Okay, so now we're going to translate. As I said, we have to translate first. You cannot reflect before translating. So we're going to move the graph 2 units to the left. And we get the following. All right, so now we're going to reflect. I'm going to replace x with negative x. And that just reflects across the y-axis. And that does not change the position of the asymptote or the appearance. Actually, it does. It's going to move it to the other side. So in this case, the asymptote actually did change positions. So we get the following graph. Again, your graph doesn't have to be perfect. So now we can find the domain and the range because we have the graph of that complicated function. We can see that the domain, which is all the x values of the points on the graph, the domain is all real numbers less than 2. Because the graph goes indefinitely off in this direction, which means the x values can be any number smaller than 2. But there's no points on the asymptote, so there's no points with an x value of 2 or an x value that's bigger than 2. So the domain is all real numbers less than 2. And in set notation, we say the set of all x values such that x is less than 2. And you can see why we use this notation, because writing in word form takes a while. In interval notation, we say negative infinity, comma 2, and make sure we have parentheses there. All right, so what about the range? The range is all the y values of the points on the graph, and you can see that the graph goes up indefinitely and down indefinitely, so y can be pretty much anything. It can even be 0. So the range, all the possible y values of the points on that graph, is all real numbers. So if you got that one right, good. Again, finding the domain can be sometimes difficult using the equation. We learned how to do it in a previous class, but finding the range is really a daunting task. Now we could find the range with the equation without graphing, but it's much easier to graph, even though we are taking a while because we're using the transformation method. But we are killing two birds with one stone because we're reviewing the transformation method, which is extremely important for the math curriculum, and we're also learning how to use graphs to find domain and range of really complicated equations. So let's try number 9 together. This is going to be a little more complicated. So we're going to find the domain and range of this equation, but again we're going to change f of x to y to make it easier for us to keep rewriting that equation. And we're going to get this -3 and the negative here on the other side of the equation so that we can graph it. So I'm going to add 3 to both sides, and then I'm going to divide both sides by -1. Actually, I'm going to multiply both sides by -1. You'll get the same result, but it's easier to think about multiplication in this case. Now we could distribute this -1 so that we have -y minus 3. That's fine, but I'm just going to leave the negative outside the sum in our notation. So now you can see that the parent function, and again we're going to call it the parent function, so I'm going to change to parent function. You can see that the parent function is the absolute value function, and I know you've graphed this many times, but my students will know the library of relations, which we now call the library of functions, and that's exactly my goal. Every student that takes this course and does exactly what I tell you to do will know the library of relations like the back of his or her hand. So now we're going to we need to reflect first. And the reason for that is that if we translate first, add 3 to y, then we'll have to put a negative in front of y plus 3. Well, the transformation properties don't tell us what to do in that situation. We could figure it out, but the transformation properties don't directly tell us. We know what to do if we write a negative in front of y and y alone, but we would have to put a negative in front of y plus 3. So we need to we need to reflect first. So that reflects across the x-axis. And what we need to do next is translate. We must translate in the second step in this case, because if we dilate first and then translate, we're going to have to replace 3x with 3x minus 1. The transformation properties don't tell us what to do when we're subtracting 1 from 3x. They only tell us what to do when we're subtracting 1 from x and x only. So we're going to translate in the next step. So we're going to replace y with y plus 3, and we're going to replace x with x minus 1. And that moves the graph 1 unit to the right and 3 down. And we get the following graph. And then we're going to finally dilate. So I'm going to replace x with 3x. So we're going to divide all the x values by 3. So this point here has an x value of 0. So we can keep that. So this point went to there. And this point has an x value of 3. So divide by 3 and we get 1. And this point right here has an x value of negative 3. So divide by 3 and you get negative 1. But we need the corner of the graph, so the x value of this point here is 1. So the new x value is going to be 1/3. And so now we're ready to connect the dots. That gives us a general idea what the graph looks like. So now we can see the domain and range. This graph goes to the right indefinitely and to the right, or to the left indefinitely and to the right. So the domain is all real numbers, and the points on the graph have y values that are all less than or equal to negative 3 because there's no points up here. This point has the biggest y value, which is negative 3. So the domain is all real numbers. And the range is all real numbers less than or equal to negative 3. In set notation, we write negative infinity, comma, negative 3, and we need a bracket because negative 3 is in the range. Whoops, that's interval notation, sorry. In set notation, we write the set of all y values such that y is less than or equal to negative 3. Okay, so that was a little more difficult because we had to move two things onto the other side of the equation. We had to move this negative here and also the negative 3 there. So let's try one more of these before you try one on your own. We're going to find the domain and range of this function. So just to make things easier, we're going to change f of x to y. And then we're going to subtract 2 from both sides. And this is where things get a little weird. We're actually going to divide both sides by 3 in order to get rid of that 3, or put it on the other side. So we subtracted 2 from both sides. Then after doing that, we then divided both sides of the equation by 3. So we've done that many, many times. You can go back to my previous, or the classes on graphing relations, or transformations in the library of relations if you want to review how to do that. So now we're ready to graph, and instead of writing parent relation, we're going to write the parent function, because now we're considering this to be a function. And the parent graph is the reciprocal function, reciprocal parent function. And of course we have our 6 reference points, and we have 2 asymptotes. You've drawn this many, many times. This is just our starting point. We cannot translate first, because if we subtract 2 from y, at some point we're going to have to dilate, so we're going to have to divide y minus 2 by 3. But the transformation properties don't tell us what to do in that case. So we're going to have to dilate before we translate. So I'm going to replace y with y over 3. and then we just multiply all the y values of the graph by 3, and that's not going to affect the asymptotes. So this point goes here because the y value of the point is multiplied by 3. And just continue to move all those points. And we'll connect the dots. Probably should plot this point also 3, 1, and -3, -1. And now we're ready to connect the dots. Okay, now we're going to reflect. So I'm going to replace x with -x. Actually, no, we cannot reflect. I just realized we can't reflect. We have to translate next. We're going to replace y with y minus 2. And we're going to replace x with x plus 4. And that moves the asymptotes 4 units to the left and 2 units up. And pretend that this is the origin now, and we have our same points. And then we can connect the dots. Okay, so now we're going to reflect. We're going to replace x with -x. And that reflects across the y-axis. So the vertical asymptote is going to move over. It's going to flip over the y-axis. And that's not going to change the horizontal asymptote at all. So all the points are going to flip across the y-axis. So this point is going to move there. And so on and so forth. Okay, so looking at this graph, we can see the domain and range. There's only one x value that is not it's not going to be found on a point on the graph, and that is this x value 4. And we could tell that just by looking at this equation. You plug in 4, you get 0 in the denominator. So the domain is all real numbers except 4. The set of all x values such that x is not equal to 4. And in interval notation, we write -infinity, comma 4, parenthesis, union symbol, 4, comma, positive infinity. Now, there are no points on the red graph that have a y value of 2 because we have this horizontal asymptote. That's the only y value that is not on the point. So the range is all real numbers except 2, the set of all y values such that y is not equal to 2. And in interval notation we write negative infinity comma 2 union 2 infinity. Okay, so I want you to take a picture of those problems. You're going to do some similar problems, and I want you to try problem number 11, and when you come back we'll do it together. Okay, we're back. As usual, we're going to change f of x to y to make things easier for us. And then we're going to put that negative symbol on the other side of the equation, and we're also going to take the 4 and put it on the other side. So I'm going to multiply both sides by negative 4. And we get this equation here. And I'm going to graph the parent function. We're going to call it function instead of relation at this point. The parent function is obviously the cubic function, and the graph looks like that. And so what do we do next? We could actually translate or dilate or reflect. It actually doesn't matter in this case. I'm going to translate first. So that moves the graph 1 unit to the left. And then I'm going to reflect. I'm going to replace y with negative y. So that reflects across the x-axis. And then I'm going to replace y with 4y. And that's going to divide all the y values of this graph by 4. So we need to find some other point. So I'm going to plug in negative 3 for x. Negative 3 plus 1 is negative 2. Negative 2 cubed is negative 8. Negative 8 divided by negative 4 is positive 2. So if you plug in negative 3, you get positive 2. So if we start from this reference point here, we move 2 to the left, we go 2 up. So if we go 2 to the right, we're going to go 2 down. So that gave us some more points there. But I'm going to plug in negative 4 now to the equation. Negative 4 plus 1 is negative 3. Negative 3 cubed is negative 27. And negative 27 divided by 4 is negative 6.75. Actually, positive 6.75. So 1, 2, 3, 4, and up 1, 2, 3, 4, 5, 6, and then 0.75. So we moved 1, 2, 3 units from that reference point to go down, or to go up 6.75. So I'm going to move 3 to the right, and then go down 1, 2, 3, 4, 5, 6.75. Oops. So that gives us, that helps us graph. So sorry about that, you had to use the equation there. But looking at this graph, we can see that the domain is all real numbers. This graph just goes up indefinitely to the left and down and to the right. So because it goes indefinitely to the left and right, the domain is all real numbers. The x values of the points on that graph can be anything. And the range also can be anything because it goes up indefinitely and down indefinitely, and y can be 0 also. So the range is all real numbers. So if you got that right, good. All right, try number 12. When you come back, we'll do it together. Okay, we're back. So we're going to replace f of x with y as usual. And then we're going to add 1 to both sides. And we're going to divide both sides by 2. So I did 2 steps in my head. You should be getting to the point where you can do that in your head in algebra. Remember, this is an intermediate algebra course. So you're going to be doing a lot in your head. Okay, so we're going to change this to a parent function. This is now, we're calling it a parent function. The parent function is the reciprocal function. And of course we have 2 asymptotes. You've graphed this many times. And we have our 6 reference points. So you should be able to graph these parent functions very quickly. And now we have to determine what to do next. Do we translate, reflect, or dilate? Well, we can't translate first because if we add 1 to y and then divide by 2, the transformation properties don't tell us what to do when we divide y plus 1. They tell us what to do when we divide y by 2 only, but we're not dividing y by 2, we're dividing y plus 1 by 2. So we can't translate first. We can dilate first. I think that's what we're going to need to do. In fact, in this case, yes, we have to dilate first. So I'm going to replace y with y over 2. And what that means is we're going to multiply all the y values of the graph by 2. Whoops, I put that one a little bit too high. Sorry about that. And there you go. So we're going to connect the dots. Okay, and then we're going to translate. We must translate in the next step. And the reason we must translate next is because if we reflect, that means we're going to replace x with negative x. But if we have to translate after that, then we're going to be subtracting 2 from negative x. The transformation properties don't tell us what to do in that situation. The transformation properties tell us what to do when we subtract 2 from x and x only. But if we subtract 2 from negative x, we don't know what to do in that case without manipulating or changing the form of the equation. So now we're going to move the asymptotes 2 units to the right and 1 unit down. And all those reference points are the same in relation to the intersection of the asymptotes. Alright, and now we're going to reflect. So we're going to replace x with negative x. And that reflects across the y-axis. So the vertical asymptote is going to flip over the y-axis. And this point is not going to change locations because it's on the y-axis. This point is going to flip around here. And this point here is going to, that's going to be here. And so on and so forth. So now we have the graph of that complicated function. And we can see the domain and the range. There are no points on that red graph that have an x value that is -2. But all the other x values, all the other real numbers are found on the x values if we look for them. So the domain is all real numbers except -2. The set of all x values such that x is not equal to -2. Negative infinity to -2, parentheses union, parenthesis, not parentheses. So there you go. The range is restricted by this part of the graph here. There's no points on the graph that have a y value of -1. So that's the only y value that's not in the range. So we say all real numbers, the set of all y values such that y is not equal to -1. In interval notation, we write negative infinity, comma, -1, union, -1, comma, infinity. So if you got that one right, good. Now we're going to go to some more complicated problems here. Let's do this one together. So as usual, we're going to replace f of x with y to make things easier for us to write. And then we're going to move three things to the left side of the equation. This negative symbol, the 2, and this other 2 over here. So we're first going to subtract 2 from both sides. And then we're going to divide both sides by -2. And I could put the negative down here, but I'm going to write it right in front of that fraction symbol. We could also write the negative up in the numerator, but we'd have to use parentheses or we'd have to distribute. You can do it however you want. But I'm going to write it next to the fraction symbol there. And we're going to call this a parent function because we're now dealing with functions. So do we translate, dilate, or reflect first? Well, in this case, we can reflect or dilate first. Let's write the parent function first. So should we dilate or reflect first? It doesn't actually matter in this case. I think I'm going to reflect first, so I'm going to replace y with -y. That's going to reflect across the x-axis. And then I'm going to replace y with y over 2. multiply all y values by 2 in that case. Remember, it's the exact opposite of what you would think. And then we're going to translate. So I'm going to replace y with y minus 2 and x with x minus 4. So that means we're going to move the graph 4 units to the right and 2 units up. So 1, 2, 3, 4, 1, 2. Whoops. So that's what the graph looks like. We might be able to find another point if we plug in 5, actually 6, we would get, actually that's off the scale, so that's our graph. It's off the window. So as you can see, this graph goes to the left indefinitely and to the right indefinitely. So the domain is all real numbers, and the range, we can see we're going up indefinitely and down indefinitely. So the range is all real numbers also. Okay, so let's try 14. We're going to replace f of x with y. So we're doing a lot of different things here. We're practicing graphing the library of functions, and we're practicing manipulating or changing the form of an equation so we can graph it. We're practicing the transformation method. We're going to add 3 to both sides and multiply both sides by -2, and I'm going to leave the -2 next to the y plus 3 rather than distributing it. But you can distribute it if you want, but you might go out of the window of your graph if you do that. So we put the -3 and then the negative and the 2 on the other side of the equation so we can more easily graph this. And we're calling this a function, so we're going to change that to parent function. And obviously the parent function is the logarithmic function. So we have a vertical asymptote. If you plug in 1 for x, you get 0. Plug in 4 for x, and you get 1. Connect the dots. Try to make your curve smooth. And so what should we do next? Well, we're not going to be able to translate first, because if we add 3 to y, we're going to have to multiply by 2 and put a negative in front, but the transformation properties don't tell us what to do in that situation. So I'm going to reflect first. That reflects across the x-axis. So the graph flips over the x-axis. And then I'm going to dilate, so I'm going to replace y with 2y. That's not going to change the vertical asymptote, but all the y values of the points are going to be divided by 2. That doesn't affect this point because the y value is 0. But this point, the y value is now going to be -1/2. So that is a vertical compression. So then we're going to translate. We're going to replace y with y plus 3. And we're going to replace x with x minus 2. So that's going to move the vertical asymptote 2 units to the right. And all the other points are going to move 2 units to the right and 3 units down. So here is our new graph. So now that we have the graph, we can see the domain and the range. There are no points that have x values that are equal to 2 or less than 2. So the domain is all real numbers greater than 2. So remember, the domain is all the x values of the points on the graph. In set notation, we say the set of all x values such that x is greater than 2. In interval notation, we say 2 comma positive infinity. Now, the range is all the y values of the graph, and you can see the graph goes up indefinitely and it goes down indefinitely. Not quite like that, but it keeps going down. So the range is all real numbers. In an interval notation, negative infinity, comma, infinity. Okay, so take a picture of those two problems. You're going to do some problems that are similar to that. So try number 15. When you come back, we'll do it together. Okay, we're back. So we're going to replace f of x with y to make things easier for us. And we're going to add 2 to both sides and multiply both sides by negative 3. And that allows us to graph the equation. So obviously this is an absolute value parent function, the old familiar V shape. And so we need to reflect or dilate first. It doesn't matter which one, but you can, I'm going to reflect first. You cannot translate first. So that's going to flip across the x-axis. And I'm going to dilate. I'm going to replace y with 3y. That's going to divide all the x values by 3. And then I'm going to translate. So I'm going to replace y with y plus 2. And I'm going to replace x with x plus 3. And that's going to move that purple curve 3 units to the left and 2 units down. Okay, so the domain is all the x values of the points on the graph. So we can see that the graph goes to the right indefinitely, and it goes to the left indefinitely, so the domain is all real numbers. But the range is restricted. There are no points up here. This point has the biggest y value, and every other y value is smaller. So the range is all real numbers less than or equal to negative 2. the set of all y values such that y is less than or equal to -2. Negative infinity to -2 with a bracket. A bracket because -2 is part of the range. If you got that one right, good job. Try number 16. Okay, we're back. As usual, we're going to replace f of x with y. And then we're going to subtract 3 from both sides and divide both sides by -5. And I'm going to write the negative next to the fraction. You can write the negative in the numerator, but then you would have to distribute the negative. Whoops. You'd have to distribute the negative to the y and to the -3. So we'd have -y plus 3. Or you could use parentheses and just keep it out in front. But I'm going to write the negative symbol in front of the fraction line. And then on the right side of the equation, we're left with 4 to the x minus 2 power. So this is a parent function, so I'm going to change that to function. And obviously we have an exponential parent function with base 4. So whenever you have an exponential function or relation, you have a horizontal asymptote, we can use the equation. Plug in 0, we get 1. Plug in 1, we get 4. And connect the dots. So we cannot translate first, so we're going to have to reflect and then dilate, or we can dilate and then reflect. So I'm going to reflect. I'm going to replace y with -y. So that reflects across the x-axis, which doesn't change the appearance of the horizontal asymptote. That flips the graph across the x-axis. Then I'm going to replace y with y over 5. That multiplies all the y values by 5. So this point has a y value of -1, so its new y value is -5. And this point is going to go way out of our window. So let's plug in an x value into the equation over here. So let's plug in -1. If you plug in -1 for x and solve for y, you get -5/4. So that's that point there. If you plug in -2 for x and solve for y, you get -5/16, which would be about there approximately. Your graph doesn't have to be perfect again. Now we have to draw the asymptote. Okay, so now we're going to translate. We're going to replace y with y minus 3. And x with x minus 2. That moves the graph 2 units to the right and 3 units up. So this point is 0, 0, 5, so that's going to move 2 units to the right and 1, 2, 3 up. And this point is -1, -5/4. That's going to move 1, 2 to the right and 1, 2, 3 up. And then we can just use the relative location of that point to find the other point. So my graph doesn't look perfect, but the graph approaches the asymptote as we move to the left. It's not really supposed to be going down like this, but you get the point. In fact, I should probably redraw that, because that's doesn't really make sense. There we go. So now we can see the domain is all real numbers because the graph moves to the left and to the right indefinitely. So the domain is all real numbers. And the range is restricted. There are no points up here, only points under the asymptote. So the y values of the points, they're going to be less than 3. So the range is all real numbers less than 3. The set of all y values such that y is less than 3. Negative infinity, comma 3 with parentheses. So if you got that right, good job. So that is the class today. If you want to take screenshots of all the work that we did to help you with homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and number 4 and number 5 and 6 and 7 and number 8. But don't go before you get your homework. Let's take a look at the homework. Here's screenshot number 1 of the homework. And number 2. And number 3. And number 4. And don't go before you get the answers to the homework. Remember, it's not enough to simply attempt the homework. You must do it completely and correctly. Here's screenshot number 1 and number 2 and number 3 and number 4. So remember, if you don't do that homework, it's a 100% guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.